Okay, let's unpack this. Close your eyes for a moment and just envision a near future. Our roads aren't just crowded, they're buzzing. Buzzing with autonomous vehicles, flawlessly navigating complex traffic scenarios, predicting every move, responding in milliseconds. Picture drones, not just delivering packages, but doing so with this uncanny accuracy, avoiding unexpected obstacles. Or consider the next generation of robots in factories, assisting workers with such precision and awareness that they enhance safety and efficiency in ways we're only just, well, beginning to imagine. What's the single indispensable element these incredibly sophisticated systems absolutely rely on for their safety, their reliability, and their astonishing efficiency? It's their ability to truly see and profoundly understand their dynamic environment, especially the ever-changing road ahead. Now, take that vision and add two critical constraints. Every split second counts, and energy efficiency is paramount. In this demanding landscape, traditional camera systems often just, well, they can't keep up. That, my friends, is the monumental challenge at the heart of this deep dive.
And that's exactly where the research paper we're diving into today steps in to revolutionize our thinking. It's titled EventASEG, an event-based asynchronous segmentation of road with likelihood attention. And it's the groundbreaking work of Lakshmi Annamale and Jatin Singh Thakur. Our mission today is to understand how this truly novel approach leverages a unique type of sensor, the event camera, and a very clever, purpose-built neural network designed to achieve something remarkable in road segmentation. This isn't just an incremental improvement. It's particularly focused on the stringent demands of time-critical and power-constrained robotic platforms.
Right, where every millisecond counts and every watt matters.
Exactly, where every millisecond and every watt of energy can determine success or failure. What's truly fascinating here is how these researchers have fundamentally rethought the way we process visual information for autonomy, moving beyond conventional methods that have, in many ways, become a bottleneck for these next-generation systems.
And this isn't just for the hardcore robotics engineers or AI researchers out there. This deep dive is directly relevant to you. Whether you're deeply interested in the future of artificial intelligence, fascinated by the nuts and bolts of how robots actually see, or simply curious about how ingenious new technologies are solving some really old, difficult problems, this deep dive offers a shortcut. A shortcut to understanding a critical advancement. An advancement that could make our roads dramatically safer, our autonomous systems significantly smarter, and frankly, our lives more seamlessly integrated with intelligent machines. This isn't just about self-driving cars either. It's about a new way of seeing that has profound implications for everything from next-gen security cameras that only report what's truly relevant to intuitive gesture recognition for smart devices. Get ready for some fundamental shifts in how we think about machine perception.
Absolutely, it's a really exciting area.
The bottleneck of traditional road segmentation. Why we needed a change.
So let's kick things off by understanding the core problem. Why did we even need a fundamental change in how autonomous systems perceive the road? At its heart, road segmentation is absolutely foundational for autonomous vehicles. It's how they see and differentiate what's drivable from what's not. Think of it as constructing an occupancy map, literally, knowing with certainty what portion of the visual scene is the road and what isn't. This critical capability underpins everything, really, from basic lane keeping to complex trajectory planning.
Right. And for simpler tasks like advanced driver assistance systems where maybe a human driver is still largely in control or in, say, controlled environments with minimal dynamic objects, just identifying the road is often sufficient. It provides those essential high-confidence visual cues for navigation without needing to analyze every single detail of the surrounding scene.
Yeah, it gives the system enough to work with for those specific tasks.
Exactly. And in the broader field of computer vision, this task is a crucial and specialized subset of what's known as semantic segmentation.
Okay, so semantic segmentation is the bigger picture.
Precisely. And to elaborate on that, semantic segmentation is the task of classifying every single pixel in an image into predefined categories. So a general semantic segmentation network wouldn't just tell you this is a road, it would tell you this pixel is part of a car, this one is a pedestrian, this one is a tree, and these are all part of the road surface.
Okay, so pixel by pixel labeling of everything.
Exactly. It's incredibly powerful, giving a machine a detailed, pixel-level understanding of its environment. But this brings us to the core problem with the traditional approach to road segmentation. Conventional camera-based systems, while functional, are inherently resource-intensive and often too slow for the real-time demands of autonomous systems. When you're trying to perform full semantic segmentation with a traditional camera, you need highly sophisticated encoder-decoder architectures.
Right, those sound complex.
They are. Conceptually, an encoder-decoder network takes an image, processes it through layers to extract high-level features, that's the encoder part, and then reconstructs a pixel-level classification map from those features, the decoder part. While brilliant for recognizing complex structures, this architectural complexity is computationally heavy. It consumes significant processing power and memory.
Which means it's slow and power hungry.
Exactly. It often fails to meet the stringent computing and real-time demands of autonomous vehicles, where decisions need to be made in mere milliseconds to ensure safety.
And it's a bit of an overkill too, isn't it? I mean, when you think about it, roads are relatively smooth, fairly evenly textured. Yes, okay, there are minor variations like shadows, changes in lighting, maybe different types of pavement, but a full-blown, incredibly complex semantic segmentation network seems like, well, a lot more than what's needed just to identify the drivable surface.
You've hit the nail on the head. It's like using a supercomputer to calculate 2 plus 2, as you said earlier. And that raises an important question. Can we achieve the goal of identifying the road with significantly less computational overhead if we tailor our approach specifically for that task?
It seems logical. We've seen efforts to lighten traditional networks, but you were implying earlier that's maybe just putting a Band-Aid on a more fundamental issue.
Yeah.
Is that right? Is the problem not just network complexity, but the input data itself?
That's absolutely fair to say. While the computational burden with traditional frame-based cameras has historically driven the development of lightweight networks, you see names like RoadNet RT, Fast RoadSeg, LFD RoadSeg. Even these optimized solutions still rely on processing dense, full frames of visual information. They're still processing every single pixel in an image, whether that pixel's value has changed or not, at a fixed rate.
Right. So if your car is stopped at a red light and the road ahead isn't changing at all.
Correct. A traditional camera system is still capturing and processing thousands, even millions, of static pixels every fraction of a second. That's a huge amount of wasted computation. And wasted power.
Which is where these event cameras come in. That sounds like a really different way of seeing.
It is, which is precisely why the emergence of event cameras represents such a significant shift, a true paradigm shift, as the paper rightfully calls it. Unlike conventional cameras that capture full, dense frames at a fixed rate, an event camera is fundamentally different. It doesn't send you a picture in the traditional sense. Instead, it operates on a completely different principle. It responds asynchronously at the pixel level only when there's a change in illumination.
Okay, so only when something changes.
Exactly. Imagine a grid of millions of tiny independent sensors. Each one only speaks up or sends a signal. When something visually significant happens in its immediate vicinity, a light gets brighter, a shadow passes over, or an object moves across its field of view.
It's like a silence-activated alarm system for pixels.
Right.
Most of the time, they're quiet, only triggering when there's a relevant visual event. That's pretty cool.
It is, and the benefits are truly compelling, directly addressing the challenges we just discussed. First, there's sparsity.
Less data.
Vastly less data overall, especially in static scenes. Because an event camera only records data when a change occurs, you end up with far less to process compared to a continuous stream of dense frames. If your scene is mostly static, you get almost no data. This directly leads to low power consumption, which is absolutely critical for battery-powered robotic platforms, drones, or any autonomous system where energy is at a premium. Every milliwatt saved extends operational time.
Makes sense. Less data, less processing, less power.
Then there's high temporal resolution. Event cameras react in microseconds, that's millionths of a second.
Microseconds. Wow.
Yeah. This allows them to capture incredibly fast motion that traditional cameras, even high-speed ones, would completely miss or just see as a blur. Imagine a rapidly approaching vehicle or a sudden darting pedestrian. An event camera can track that movement with unprecedented detail. And finally, they boast high dynamic range, meaning they can handle extreme lighting conditions far better than conventional cameras.
Ah, like driving out of a tunnel into bright sun.
Exactly that scenario.
Yeah.
Or navigating through deep shadows and bright patches simultaneously. A traditional camera would often be over or underexposed in parts of the image, losing crucial information. An event camera, however, continues to report changes with high fidelity across these challenging conditions.
Okay, so sparsity, low power, high speed, high dynamic range.
Know what I mean?
It sounds like the perfect sensor. But you mentioned there was a gap.
Right. Despite all this immense promise and the clear advantages, there is a critical unfilled niche. While researchers had indeed done pioneering work on event-based semantic segmentation, attempting to classify multiple objects from event data and conventional cameras had made significant progress in general road segmentation, there was a glaring absence. Dedicated models tailored specifically for binary road segmentation using event cameras were largely unexplored. And here's the crucial challenge.
How to actually use that sparse data effectively.
Precisely. Simply adapting that sparse, asynchronous event data to conventional neural networks usually involves accumulating these events into 2D grids, effectively recreating a frame of sorts. But doing that immediately reintroduces latency, forces synchronous processing, and leads to unnecessary computations. You end up negating many of the event camera's core advantages.
By trying to make it act like a regular camera again.
Exactly. You're trying to force its unique data into a traditional framework. This gap, this unmet need or missing piece in the research, is precisely what EventASEG aims to fill. It's about developing a new way of processing that truly respects the unique, event-driven nature of the data.
Introducing EventASEG, a lightweight, event-driven solution.
Which brings us directly to EventASEG, the paper's brilliant proposed solution. They call it an event-based asynchronous segmentation network. And it's designed specifically for road segmentation, but with this philosophy centered on being incredibly lightweight, and interestingly, it's decoderless and transformer-based. That sounds quite targeted.
It is. Very targeted. This is a specific approach aimed at tackling the binary task of distinguishing road from non-road with maximum efficiency, making it incredibly well-suited for the challenges we just discussed. And EventASEG's core architectural innovations are what truly allow it to leverage the event camera's benefits, rather than just forcing the data into old paradigms. There are two key contributions that make it so efficient. First, it employs sparse processing. This means it works only on pixels with events. It's not wasting computation on static parts of the scene where nothing is changing.
So if the road isn't changing, it doesn't process it.
Correct. Think about it. If the road ahead is perfectly still, why keep processing it? EventASEG only processes the parts that are dynamic, where actual visual information is emerging. Second, it uses event-driven processing, meaning it's triggered only by event occurrences. It reacts immediately to changes as they happen, as soon as an event is detected, rather than waiting for a fixed frame rate like traditional cameras.
So no waiting for the next frame. It just reacts.
Exactly. This design inherently eliminates the need for accumulating events into those dense artificial frames we discussed earlier. By doing so, it cuts down computational complexity significantly because the network is only active when there's new information to process.
So it's like having an intelligent system that only processes the highlights reel of reality, rather than constantly filming and then trying to sift through every single frame. That's a massive shift in how data is processed.
It really is. Leads to incredible efficiency gains right from the input stage.
Yeah.
However, this sparse event-driven approach does come with a critical challenge. Raw event data, by its very nature, provides limited contextual information compared to a dense image frame.
Right. A single event is just a blip, isn't it? Where it went brighter or darker, not much else.
Exactly. A single event just tells you where and when something changed, and by how much. It doesn't give you the rich surrounding visual context that a full image provides, making it hard to understand relationships between events. This is where EventASEG's elegant solution truly comes into play. It equips its transformer architecture with a novel likelihood attention mechanism.
Likelihood attention. Okay, that sounds key.
It's absolutely key to interpreting those sparse events effectively. It allows the network to build a more coherent understanding of the scene from minimal data points. It's about intelligently inferring context from the bits and pieces it receives.
Got it. So it helps piece together the puzzle from those sparse clues. And it's important to emphasize the scope here, right? While EventASEG isn't designed for that complex multi-class semantic segmentation, differentiating dozens of objects.
Correct. That still needs those more sophisticated, resource-hungry architectures we talked about.
It absolutely excels in binary road segmentation, just road versus not road.
Precisely. And this makes it ideal for a very specific but critical set of scenarios where low latency and low computation are not just nice-to-haves, but imperative.
Like those time-critical, power-constrained robots you mentioned.
Exactly, where every watt of power and every microsecond of processing time can make a real difference in performance, safety, and operational longevity. It focuses its strengths where they are needed most.
Deconstructing EventASEG's architecture, how it works.
All right, let's pull back the curtain a bit and conceptually deconstruct EventASEG's architecture.
Yeah.
We need to start with the very building blocks, the raw event data. The fundamental unit here is what we call an event. Let's denote it as E. And it's essentially, as you said, a precise digital whisper from a single pixel. This event is captured as a four-dimensional vector, Gelki Chi T.
Correct.
Let's break those components down conceptually. Are simply the exact pixel coordinates on the sensor where that specific change occurred. So where on the grid did this happen? Pretty straightforward.
Like the location.
Pi is the polarity, which tells us whether the intensity at that pixel increased, represented by +1, or decreased, represented by -1. So was it a brightening or a darkening event?
Got it. Brighter or darker.
And Ti is the timestamp, often measured in incredibly tiny units like microseconds, indicating precisely when that change happened.
Microseconds again, super precise timing.
Extremely precise. And if we connect this to the bigger picture, these tiny asynchronous signals are the only input the network gets. There's no image to look at to these rapid-fire reports of change.
Which makes the interpretation task really unique. Right?
Absolutely unique. It requires a fundamentally different approach compared to processing dense image frames. EventASEG has to build its understanding of the world from these discrete, instantaneous points of information.
So how does EventASEG take these incredibly granular, sparse events and translate them into something a neural network can actually process and understand? What's the first step?
The first step is what they call an event data encoding block. This block takes a sequence of these raw causal events, these XYPT whispers, as its input. Its job is basically to project each four-dimensional event into a much richer, more meaningful digital representation. Think of it as enriching the data.
Adding more descriptive features.
Exactly. Adding more descriptive features so the network has a better handle on what each event signifies in the context of others. And crucially, this encoding block also introduces a vital piece of information: positional context. It doesn't just treat each event in isolation.
Ah, so it considers the sequence.
Right. It understands that the order and relative timing of events within a short sequence can be incredibly informative. By adapting standard deep learning techniques, it adds information that helps the network understand where each event sits within the stream, not just in space, but also in time.
Which helps figure out motion, I guess.
Precisely. This is key because it helps the network characterize an object's motion. If a series of events happen sequentially across neighboring pixels, the network can start to infer movement, which is essential for understanding dynamic scenes and, of course, figuring out where the road is or isn't.
Okay, so encoding adds context and handles the sequence. What happens next? Where does the main processing happen?
Once that initial encoding is done and the raw events have been transformed into these richer, context-aware digital representations, the data moves into the core processing engine. The architecture consists of several feature extraction blocks stacked sequentially. You can think of these blocks like stages of an investigation.
Getting deeper with each stage?
Kind of. They're progressively designed to capture increasingly complex structures and patterns from the continuous event string. Inside each of these blocks, there's a sophisticated multi-head attention module and a feed-forward network.
Okay, attention. That sounds like the transformer part.
It is. This is where the magic of the transformer architecture begins to happen, allowing the network to weigh the importance of different events relative to each other, sifting through the noise to find meaningful connections.
And this is where that special likelihood attention comes in.
Exactly. Now, this is truly the star of the show. EventASEG's unique likelihood-based self-attention mechanism. Let's contrast it with standard attention for a second.
Okay.
In a standard transformer, attention essentially tells the network how much to pay attention to other parts of the input sequence when processing a specific element. It helps establish relationships based on, abstract feature similarities.
Right, like which words are related in a sentence.
Sort of, yeah. But with sparse event data, a critical challenge arises. A single event lacks broader context. It's just that tiny blip. How do you get a meaningful understanding of a scene from scattered points? EventASEG's innovation is that it doesn't just look at the abstract features of events when calculating attention. It intelligently weaves spatial information, the actual X and Y coordinates of each event, directly into how it decides what to pay attention to.
Ah, so it uses the location data in the attention calculation.
Precisely. The intuition behind this is incredibly powerful. It's about estimating the probability that one event is relevant to another, while also considering how close they are in physical space. It's not just what happened, but Where did it happen in relation to other events? This is how they effectively provide crucial context in a naturally sparse data environment.
Okay, that makes a lot of sense. Context from proximity.
Exactly. It allows the network to build a coherent understanding where others would just see scattered noise. It's like the network isn't just listening to whispers, but also watching the body language of the scene, allowing it to infer crucial relationships from minimal data points.
That's a fantastic analogy. Like if you're trying to figure out what someone's doing, you're not just listening to their words, but also watching where their hands are moving and how they're positioned. It adds crucial context and helps you understand the whole picture, even if you only have bits and pieces of information.
Couldn't have said it better myself. It's a very intuitive way to bring that spatial relationship into the decision-making process, especially when your input data is so inherently fragmented.
So after all that intricate feature extraction and this clever likelihood attention processing through these multiple blocks, what's the final step? How does it actually decide road or not road?
Right. After the feature extraction blocks and some additional standard processing steps like layer normalization for stability, the process features move into the final stages. They pass through a couple of dense layers. Think of these as further refining the high-level features, getting them ready for the final decision. Finally, these refined features are fed into a classification layer. This is where the network makes its ultimate prediction for each event. Is it road or non-road?
The moment of truth.
Exactly. It's where all the complex processing culminates in a simple binary decision for every single detected change that was fed into the network.
The proof is in the performance experimental validation.
All right, so we understand the architecture, the ideas behind it. Now, for the moment of truth, as you said, the experimental validation. Does it actually work? How well?
It does. The proof, as they say, is in the performance, and EventASEG delivers quite impressively. The researchers conducted their experiments on two publicly available datasets specifically designed for event cameras, DSEC semantic and DDD72.
Very standard benchmarks.
Yes, well-regarded datasets in the field. And it's important to note something specific here. These datasets originally contained multiple semantic labels, but for these particular experiments, they were merged into a binary road-non-road classification.
Ah, so they simplified the ground truth to match EventASEG's specific task. Makes sense for a fair comparison.
Exactly. This allowed for direct and fair evaluation of EventASEG's specialized capability. For implementation details, they followed standard practices, normalizing the input data, T, P, X, Y, using established weight initialization techniques, and training the network with the Atom W optimizer over 15 epochs. Crucially, they fed a small fixed number of event samples and events into the network, and they found the optimal value for N was 50.
Only 50 events at a time. That seems tiny.
It is tiny, and that's the point. This setup was designed to truly test the system's responsiveness and efficiency, seeing how well it could make decisions based on a very limited, almost instantaneous burst of event data. The loss was computed against the ground truth label available at the end of a 50 meters interval, but the input was just those 50 events.
And how did it stack up, especially since you said it's kind of the first of its kind for this specific task?
Right, that's what's unique here. EventASEG is actually the first system of its kind to provide event-level segmentation of roads, directly from the raw event stream. This puts it in a category of its own. So to compare its performance, the researchers had to get creative. They retrained several state-of-the-art semantic segmentation techniques, names like EvSegNet, ViaD2E, EvSegFormer, even MaxII-Former specifically for this binary road segmentation task.
So they adapted existing complex methods to do the simpler binary job.
Correct. And a key point to understand is that these other methods often required accumulating events into 2D grids as per their original designs. This effectively forced them to operate in a more traditional frame-like manner.
Which, as we discussed, kind of defeats the purpose of the event camera.
Exactly. It immediately puts them at a disadvantage when it comes to leveraging the true benefits of event cameras, low latency, and sparsity. The results, as detailed in Table 1 of the paper, are quite clear. EventASEG achieves state-of-the-art performance in terms of accuracy and mean intersection over union, or MIOU, for this binary road segmentation task.
So it's as good as or better than the complex methods adapted for this task.
Yes. What's particularly striking is that it performs comparably to these much more complex, often frame-based networks, but with its significantly simpler decoderless design. And the critical differentiator, as we've highlighted, is that EventASEG operates directly on raw events in real time, processing just those 50 events almost instantly. Unlike these other methods that typically rely on some form of event-to-frame conversion, which inevitably adds overhead and latency.
So it gets the same or better accuracy without all the computational baggage and delay. That's pretty significant.
It is. It really validates their approach.
Okay, so we've established it's accurate. But what does this all mean for real-world applications? This is where EventASEG truly stands out and shines, right? The efficiency aspect.
Absolutely. It's not just about matching performance. It's about how it gets there and the profound implications of that efficiency. Let's talk about efficiency, starting with the stark contrast between event-driven versus traditional frame-driven processing. We can see a dramatic difference in power efficiency due to EventASEG's dynamic resource allocation.
Because it only processes changes.
Precisely. Traditional frame-based methods, like EvSegNet, always process a fixed, large volume of data within a given time period. For instance, for a typical 640 by 480 three-channel image, they would process something like 1.8432 million data points every 50 milliseconds.
Wow, that's a lot.
It is. And crucially, regardless of how much activity is actually happening in the scene, it's like constantly refreshing an incredibly detailed painting every few milliseconds. Even if only one tiny brushstroke changes, that's a massive continuous computational drain.
And a power drain, too.
A huge power drain. EventASEG, in contrast, dynamically allocates resources. The number of data points it processes varies based entirely on the scene's dynamics. In their experiments, this ranged from a mere 1,700 events to about 32,000 events within that same 50 millisecond interval. The average number of data points processed by EventASEG is approximately 10,200.
Okay, so 10,000 versus nearly 2 million.
Orders of magnitude less data processed, sometimes as little as 0.5% or 1% of the data compared to traditional methods.
That's incredible.
It translates directly to truly significant power savings. Absolutely crucial for battery-powered robots, drones, autonomous vehicles, anything that needs to operate for extended periods without recharging. Imagine a delivery drone that can fly for hours longer.
Or a car with significantly better range just because the vision system is more efficient.
Exactly. Reducing its environmental footprint, too.
That's a truly profound difference. Your analogy earlier about filming a static wall versus only highlighting when a fly lands, that really hits home now?
It's a fundamental shift. And that efficiency also translates into a dramatic, potentially life-saving reduction in latency.
Right, the speed factor. How much faster are we talking?
Traditional event segmentation algorithms, by accumulating events over a time interval to, say, 50 milliseconds to form those 2D grids, inherently introduce a minimum latency equal to that interval, so 50 milliseconds of delay before you even start processing. EventASEG, by only accumulating that small number of events, N50, demonstrates negligible latency. We're talking consistently ranging from just 1 to 10 microseconds.
Microseconds, not milliseconds.
Microseconds. That's thousands of times faster than the 50 milliseconds typical of frame-based approaches.
Wow. Okay, that really drives home the point.
It does, and it raises that important question. In a safety-critical system like an autonomous vehicle, how much is 50 milliseconds worth?
A lot in terms of reaction time.
A huge amount. A car traveling at just 60 miles per hour covers nearly 4.5 feet in those 50 milliseconds. That's additional stopping distance just from processing delay. In a critical situation, that small difference can literally be the difference between avoiding an accident and not.
So EventASEG's near instantaneous reaction time significantly enhances the safety margin.
Dramatically enhances it.
And beyond the event-driven processing, the architecture itself being decoderless, that helps too, right?
Absolutely. The decoderless architecture offers significant practical advantages. EventASEG requires a minimal number of parameters. We're talking in the low millions and fewer GFLOPs, or gigafloating point operations per second, a measure of computation, compared to other state-of-the-art segmentation networks. This is shown very clearly in the paper's Table 1.
Less complex, fewer calculations.
Exactly. And this reduced complexity directly leads to much faster inference speeds when running on real-world hardware, like an NVIDIA GeForce RTX 3090 GPU. Faster inference means quicker decision-making for the autonomous system, which, again, is paramount for real-time applications where every moment counts.
Faster, safer, more fluid operation.
That's the goal.
Okay, so the paper also mentions ablation studies. You mentioned these earlier. They help figure out which parts are doing the heavy lifting.
Exactly. Ablation studies help researchers understand which parts of their design contribute most to performance. It's like systematically taking parts out to see what breaks or improves. In their ablation studies, they first looked at the optimal value of N, the number of events accumulated. They experimented with different values, 10, 25, 50, 100 events. They found that while increasing n from 10 to 50 initially improved accuracy in MIOU, because more events provide slightly more context, the performance gain largely stagnated when n was increased beyond 50.
Diminishing returns.
Right. Increasing n beyond 50 mainly just increased latency without a proportional accuracy boost. So N50 was chosen as the sweet spot, the optimal balance between achieving good performance and maintaining that incredibly low latency, maximizing the event camera's advantages.
And what about that likelihood attention? How much difference did that make?
That was critical. They did a direct comparison, running the model with and without their novel likelihood attention mechanism. The results showed that this custom attention mechanism significantly enhances the performance of road segmentation.
So it really works.
It really works. It's the key innovation that allows the network to build context effectively from those sparse events. And, crucially, this performance boost comes with only a minimal increase in computation.
Oh, no.
Just a few extra mathematical operations, 2 additions in the numerator and 2 n additions in the denominator of the attention calculation based on their equations. It's a highly efficient way to gain that crucial contextual understanding without adding significant computational overhead. Smart design.
Very smart. And they also compared it to a wider range of conventional networks.
Yes, the paper includes an extended comparative analysis, putting EventASEG up against an even broader range of conventional, often frame-based networks like SegFormer, PSPNet, DeepLab v3, FCN, and MobileNet v3. This really helps to contextualize its performance within the wider field.
How did it fare against those established giants?
Very well, especially considering its lightweight nature. The qualitative comparison, looking at the visual results presented in Figure 5 of the paper, is quite telling. EventASEG exhibits lower rates of false positives compared to many conventional algorithms.
Meaning fewer mistakes about what's road and what isn't.
Exactly. It's more accurately identifying the road and doing a better job of avoiding misclassifications of non-road elements. It's less prone to mistaking, say, a shadow for a pothole, or a curb for the drivable road. That's vital for safety. Quantitatively, the numbers further reinforce this. EventASEG either matches or outperforms most of these state-of-the-art methods in accuracy and MIOU, all while maintaining that far lower computational complexity.
So even against the big names.
Even when compared to top performers like SegFormer and DeepLab v3 plus Orde, EventASEG achieves similar accuracy with significantly less computational burden. This really underscores the efficiency gains without sacrificing precision. It's a truly powerful and practical solution for its specific task.
Beyond road detection, broader implications and future directions.
Okay, so we've covered the how and the what of EventASEG and seen the really impressive performance. Let's shift our focus now to the bigger picture. What are the immediate impacts and benefits? And maybe more excitingly, where might this technology take us in the broader landscape of AI and robotics?
Well, at its core, as we have established, EventASEG offers state-of-the-art road segmentation specifically for binary tasks in resource-constrained scenarios. Unparalleled speed, unparalleled efficiency. Its immediate impact is to enable safer, more responsive autonomous systems where every millisecond and every watt counts. That's a tangible leap in operational capability for next-generation platforms right there.
But you hinted it could do more than just roads.
Absolutely. The true beauty of EventASEG's architecture, I think, is its versatility. While optimized for roads, its underlying principles that sparse, event-driven processing combined with clever attention for context can potentially be applied to a wide variety of other binary classification and segmentation tasks.
Like what? What else could benefit from this super fast, low-power approach?
Well, think about things like obstacle or pedestrian detection for autonomous vehicles. Instead of constantly processing the entire scene to find them, an EventASEG-like system could potentially just quickly and efficiently detect the presence or absence of these critical elements, reacting instantly to any change, any movement.
Okay, so quick is something there. Checks.
Right. Or consider lane segmentation and road closure detection, providing real-time binary feedback on drivable lanes or blocked areas. Simple yes-no answers delivered instantly. It could be used for construction zone detection, rapidly identifying hazardous or off-limits areas, or maybe presence-absence detection of animals on the road, or vehicles in a restricted zone for surveillance.
So lots of safety and monitoring applications.
Definitely. And beyond vehicles and roads, imagine visual wake word detection for smart devices. Instead of listening for a voice command, maybe a device could detect a specific visual cue, like a hand wave, to activate using minimal power.
Ah, interesting, like a visual, hey Siri.
Sort of. Or hand gesture detection more broadly, enabling new kinds of human-computer interaction, maybe a simple thumbs-up-down for binary commands, recognized instantly by a low-power event camera system. Think anomaly detection or motion detection for surveillance or industrial monitoring, where the system only reports an alert when something new or unexpected enters the scene, rather than streaming constant static video.
That would drastically reduce false alarms and, again, power consumption for always-on monitoring.
Wow. Here's where it gets really interesting. Thinking beyond roads, this could transform everything from smart home interfaces that react instantaneously to specific gestures.
Enabling precise, low-power control without needing a remote. Or those industrial safety systems you mentioned, immediately flagging any unexpected movement in a hazardous area, providing near instantaneous alerts. The applications are truly vast.
They really are. It enables truly responsive and efficient intelligent systems that are always on alert, but only truly active and consuming significant power when necessary. It's important, though, to provide a balanced view. We need to acknowledge the limitations.
Okay, what's catch?
While EventASEG is incredibly powerful and efficient for these binary tasks, its current limitation, as the paper openly acknowledges, is that its performance deteriorates with an increase in the number of classes from multi-class semantic segmentation.
So it struggles if you ask it to identify many different things at once?
Yes, it's an inherent challenge right now. The complexity of multi-class tasks, which require differentiating between many different types of objects, not just road and on-road, but also cars, pedestrians, signs, buildings, cyclists, etc., simply demands more sophisticated architectures than the lightweight decoderless design of EventASEG currently offers.
Why is that? Why does adding more classes make it harder for this architecture?
Well, assigning a unique label to every pixel in a complex scene requires building a much richer, deeper feature representation. You need to capture subtle differences and relationships between many object types. EventASEG, in its current form, optimized for speed and efficiency on a binary task, just isn't built to develop that level of complex, multifaceted understanding across numerous categories simultaneously. Its strength is its focused simplicity.
Okay, so it's a trade-off. Speed and efficiency for binary tasks versus the complexity needed for multi-class.
Exactly. However, the paper itself acknowledges this limitation and explicitly states that this challenge will be thoroughly explored in future research. This suggests clear avenues for further development. Perhaps future work could build upon EventASEG's core principles of efficiency while strategically adding more robust multi-class capabilities. Maybe hell-arbit approaches, it's not necessarily a dead end, but perhaps a stepping stone toward even more powerful, yet still efficient event-based systems down the line.
So, to bring it all together then, we've taken a really deep dive into EventASEG and seen how it represents a significant leap forward in machine perception, particularly for autonomous systems. It offers state-of-the-art binary road segmentation with absolutely minimal latency, we're talking microseconds, and dramatically reduced computational complexity and power use. And it achieves all this by cleverly processing raw event data, respecting its sparse nature, and using that innovative likelihood self-attention mechanism to build context where traditional systems might just see noise. We've seen how event cameras themselves are fundamentally changing the game, allowing systems to see with unprecedented speed and efficiency. And how EventASEG is really leading the charge in making that practical for critical real-time tasks like road detection.
Absolutely. Yeah. And if we connect this to the bigger picture, the core insight for you, the listener, is this. By truly tailoring a network to the unique properties of these revolutionary event cameras, researchers can overcome the long-standing limitations of traditional vision systems. They can achieve breakthroughs in both performance and efficiency that simply weren't possible before. This deep dive really shows us that sometimes, maybe often in engineering, less is more.
Less data, less computation.
Right. Less data processed, less computation expended, but resulting in a much more effective, near real-time understanding of the dynamic world around us. It's about working smarter, not harder, with the data to enable this whole new generation of intelligent machines.
Which leaves us with a truly provocative thought for you to mull over as we wrap up. Given how EventASEG slashes latency down to microseconds and dramatically cuts power consumption, how might these ultra-nimble, event-driven systems change the fundamental design of future autonomous vehicles themselves? Could they lead to completely new hardware architectures? Maybe allowing for more localized, faster decision-making right there at the sensor level, rather than relying on massive central processors. Decentralized intelligence, perhaps.
That's a fascinating possibility.
Or even more broadly, how might this technology completely alter how we interact with all our smart devices?
Yeah.
Moving towards truly instantaneous visual recognition that's always on, always aware, but never draining power, reacting seamlessly to a mere flick of the wrist, a subtle shift in your gaze, or the slightest visual cue you offer. The implications for a world that's constantly but intelligently seeing seem pretty profound.
They really do. Lots to think about.
Definitely something to ponder as you think about the accelerating future of AI and robotics. Until next time, keep diving deep.